Okay, so this week we're going to talk about the t-test for two related samples in Chapter 11, and in Chapter 12 we're going to talk about analysis of variance. So a repeated measures design, or what they call a within subjects design, is one where the dependent variable is measured at 2 or more times for each individual in a single sample. So we have one group measured over a length of time. And it's the same group of subject is used in all of the treatment conditions. So the main advantage of using this is that it uses the same individuals in all treatment conditions, and so there's no risk that the participants in one treatment are substantially different from the participants in another because they're the same people. And the T-statistic for a repeated measures design is structurally similar to the other T-statistics we've examined. The major distinction of a related samples T is that it's based on the difference scores rather than the raw scores. So we say we have a group of students that we test in September and we test them again in December. We do the t-test on the difference between the September test and the December test, not on the raw scores themselves. All right, so the difference score for each individual is computed by just subtracting time 2 minus time 1, where x1 is the person's score in the first treatment and x2 is the score in the second treatment. So you can see before medication, after medication, the difference. We would sum this difference score, divide by the sample size to get the mean difference. And then we would do a t-test on that mean difference, but the computer will do that for us. So for a repeated measures study, the null hypothesis states that the mean difference for the general population is 0. So we say the mean difference is equal to 0. And the alternative two-tailed test is that the mean difference is not equal to 0. The single sample T statistic formula is the same. It's the mean minus the hypothesized mean over the standard error of the mean. And it's all calculated exactly the same way. We're just going to use the computer. So let's look at an example. A major oil company would like to improve its tarnished image following a large oil spill. Its marketing department develops a short commercial and tests it on a sample of n equals 7 participants. People's attitudes about the company were measured with a short questionnaire both before and after viewing the commercial. The data are as follows. So you can see person 1, and they didn't have any kind of impact. The commercial or advertisement didn't have an impact on them. The second one, you could see that they had an improved opinion of the company after seeing the commercial. This guy had a pretty significant improvement. They were all positive. These guys had no change. So the way I enter this into a SPSS is I just take the pre-score and the post-score, and there's no categorical variable here for groups because it's the same group of people. So our research question is, does reaction to the advertisement differ? And here we have the null and the alternative hypothesis. So the null says the mean difference is equal to 0. There is no difference in reaction to the advertisement. The alternate is that the mean difference is not equal to 0. There is a significant difference in reaction to the ad. We're still showing you the way the hypotheses are written out with Greek letters. I'm going to continue to show you that, but we're going to move away from that and just write our hypotheses out with words. Step 2 in the hypothesis testing is set the significance level, alpha level is equal to 0.05. That's always standard. Step 3 is to calculate the test statistics. So we go to analyze, compare means, and it's paired samples t-test, and that's just something I want to make a quick note about. You will see this referred to with a bunch of different vocabulary words. Dependent samples t-test, paired samples t-test, repeated measures t-test. They're all mean the same thing. So here I have the pre-score and the post-score, and I just click the pre-score, click the arrow, it brings it over here, click the post-score, clicks the arrow, brings it over here, and that's all I have to do. I'm going to say OK. I don't have to click options or anything like that. And what it does is it gives me the mean for the pre-score and the mean for the post-score. It gives me this correlation, which we didn't ask for, but they use that to calculate the confidence intervals, which is something that we get in output, and what it basically means is that we are 95% confident that the test statistic that we find that the actual mean is somewhere between negative 6.2 and 2.4. One thing to note is that if these confidence intervals span 0, which they do here, negative and a positive, then you can tell just by looking at the confidence intervals that there's no significance. I can also look over here, and it's close, but it's not quite there. It's 0.07, so we are not significant. The p is not low, so the null stays. All right, so we want to calculate the effect size, and the way we do that is we take the mean difference from output. So the mean difference is -3. We're just going to use the absolute value. So 3 over the standard deviation of the first one plus the standard deviation of the second one over 2. And I get 1.15, which is a large effect for a non-significant finding, but that's just, it is what it is. And then we have this other thing called coefficient of determination. When you, and I've talked about this with the independent samples t-test, r squared, when you do correlation, you just get r. If you square it, you get this coefficient of determination. But I can take my t statistic that I found here, which was -2.2, and take the absolute value. I say 2.2 squared over 2.2 squared plus the degrees of freedom. I get r squared is equal to 0.45, which represents 45% of the variation in the agreeableness score is attributed to the advertisement. So the way they feel about the company is that agreeableness score, and the independent variable is whether or not they saw, or is that they saw the advertisement. And so we would report our report our findings out in APA. T of 6 degrees of freedom is equal to -3, P is equal to 0.07, Cohen's D is equal to 1.15. All right, let's look at another example. In a study to determine if swearing can help alleviate the feelings of pain, each participant was asked to plunge their hand into a bucket of ice water and keep it there as long as pain would allow. In one condition, the participants repeated their favorite curse words while their hands were in the water. In the other condition, the participants repeated a neutral word. In addition to lowering the participants' perception of pain, swearing is also increased the amount of time that they were able to tolerate the pain. This experiment was repeated and the data are shown on the next slide. Are the differences still significant? Well, first question is, why is this a repeated measures or a paired samples t-test when they're not doing it at 2 different times? It's not like a pre-test and a post-test. Well, the answer is because they're giving the same group of people 2 different conditions. So let me go to the next slide and show you. What they're doing is this person was given swear words and they measured it in seconds, how long they were able to keep their hand in the water. Then this person at a later time was given neutral words and measured how long they were keeping their hand in the water. And they did that for each participant. So it's a paired samples t-test because it's 2 different conditions but the same person. So I just go in and I put the swear words and the neutral words. This is time in seconds, okay? It's just, this is the condition and this is the condition. The null hypothesis is, well, first of all, the research question is, does tolerance of pain differ based on word uttered? The null and the alternative hypothesis is that there is no difference in time and bucket. There is difference in time and bucket. The alpha is always 0.05. I do the same thing, compare means, paired samples t-test. I've now, to my data set, added these variables, and I move over swear word and neutral word. I click OK, and I can see that, yes, there is significance. The mean difference, so swear word folks were able to keep their hands in the water almost 14 seconds long, well, 14 seconds exactly longer. And I can see here at the confidence interval that it does not span 0, so I can tell just by looking at that it's significant. I come over here and I see, yes, it is indeed significant. And here's our mean difference is 14. Okay, so I come and calculate my effect size. I've got the mean difference, which I get from here is 14. I get the standard deviations from the 2 groups over here, not the standard errors, but the standard deviations. Divide by 2 and I get 0.686, which is a medium to large effect size for Cohen. The coefficient of determination, I calculate it out. I get the mean difference squared over the mean difference squared plus the degrees of freedom, and I get 0.0956, so 9.56% of the variation in the time and bucket is attributed to the type of word uttered, and then I write it out in APA. And since my p-value was 0.004, I could have done it as p is equal to 0.004, but I just chose to do it as less than 0.01, and that's fine. Okay, let's move on to Chapter 12, Introduction to the Analysis of Variance. So an overview is that ANOVA, so you get analysis of variance, is where we get ANOVA, is a hypothesis testing procedure that's used to evaluate the mean differences between two or more treatments or populations. So if I just had two, I could do this as effectively with an independent samples t-test, but once I throw in another group, I have to use analysis of variance. I can use analysis of variance for two groups, but it would be easier just to use a t-test. So as with all inferential procedures, ANOVA uses sample data as the basis for drawing general conclusions about populations. I beat a horse on this one. I say this all the time. These are inferential statistics used to make inferences back to the general population. A major advantage of ANOVA is that it can be used to compare more than two treatments. Okay, so let's look. Okay, so here's a typical situation in which one-way ANOVA would be used. We have three different populations with three different means. In population 1, they received treatment 1. Population 2, they received treatment 2. Population 3, they received treatment 3. I pull a sample from that population of 15. I see that their mean is 23. These guys, their mean is 28. And these guys, their mean is 20. That's the sum of squares. We don't need to worry about that. So what I want to know is there a difference among these three groups? And I see that we have different means. This one may be significantly different, but we're not sure yet. We have to do. Okay, so just a little bit about vocabulary. In analysis of variance, the independent variables are called factors, and each factor has a number of levels. So these factors are categorical or nominal. That's our independent variable. So for example, if we say we have 2 factors of gender, we know it's male and female. Say we have 4 factors of ethnicity. We have black, white, Hispanic, and Asian. Okay, so in analysis of variance, there are the independent variables are called factors, and each factor has however many levels it has. So a factor is a nominal or categorical variable, and if I'm talking about gender, it has 2 levels, male and female. If I'm talking about ethnicity, depending on how many I have in my group, it might be 4 or 5 levels. In this chapter, we're only going to cover one-way analysis of variance, which means we have one dependent variable. It's also called an outcome variable. One dependent variable and one independent variable. But there are ways we could do a 2-factor design, or what they call a factorial design, where you have 2 independent variables and you're assessing the outcome variable on those 2 different ones, like gender and ethnicity. I want you to know that those exist, but we're not going to do that type of ANOVA. We're just going to stick with one-way analysis of variance. So, in general, the null states that there is no treatment effect. So in an ANOVA with 3 groups, the null could appear like this. The null of mean of the group 1 is equal to the mean of group 2 is equal to the mean of the group 3. The alternative hypothesis states that the population means are not all the same. So I could rewrite this with not equal signs here, or I often just see there is at least one mean difference, because if this one is not equal to this one, then we will have a significant ANOVA overall test. All right, so let me just reiterate. Analysis of variance, ANOVA, comes from here, an ANOVA. It's a hypothesis testing procedure that is used to evaluate the mean differences between 2 or more groups. We're just going to say 3 groups or more. The independent variable is categorical and is called a factor, and the dependent variable is continuous. It's interval or ratio. You cannot say causal relationships cannot be assumed. This is a question where we would want to know impact, whether race or ethnicity impacts math achievement, or whether 3 different teaching methods impact reading achievement. This is a differences in groups type question. So why do we do this ANOVA and not just a bunch of t-tests? So remember when we talked about type 1 error, the pregnant man, the false positive? As we increase the number of t-tests, we increase the risk of making a type 1 error. So these are mistakes we make when we say the null hypothesis is false when it is not. It is the incorrect rejection of a true null hypothesis, otherwise known as a false positive. So we could make errors if we just do a t-test between group 1 and 2, and then a t-test between group 2 and 3, and then a t-test between group 1 and 3. We have an inflation of risk to make a type 1 error, so we do this calculation, this ANOVA, in order to eliminate that risk. So as with all statistics, we have some assumptions, and as we get more complicated in our analyses, the assumptions will become a little bit more involved. So the first one is that each group sample is drawn from a normally distributed population. And that one we're just going to assume. All populations have a common variance, and we've seen the Levine's test in the independent samples t-test. We're going to see it again here. All samples are drawn independently of each other. So if I'm in group 1, I'm not also in group 2. And then within each sample, the observations are sampled randomly and independently of each other. We're just going to assume that as well. And then this factor effects are additive. That has to do with the factorial. I probably should take that from this slide. Okay, so before we've been talking about a t statistic, and now we're talking about an f statistic, which is a ratio of 2 variances. This is not something you'll need to know specifically for a test or something, but I just want you to know where they come from. So what it does is that it's looking at the variance, which is the difference between the sample means, and then over the variance, which is the difference within the sample means. Because now that we have 3 groups, we want to know, is there a difference among the 3 groups? But also we have to deal with the fact that there may be difference within our group, within each group. So we call this the difference between over the difference within. And then we know that the F statistic can't be 0, because when you divide something by something else, you may get close to 0, but you're not going to get 0. You can't divide by 0. When F is equal to 1, there is no significance. Now we have numerator degrees of freedom and denominator degrees of freedom, because we have number of groups up here and then number of people within the groups here. Okay, so the F distribution looks different when and then you have to account for the degrees of freedom for the numerator and the degrees of freedom for the denominator. So this red line starts up at infinity and positive infinity and goes toward positive infinity on the x-axis. And as we increase our sample size, you can see, again, because of the central limit theorem, that it becomes more and more normal. And we also see that it can't be 0. Okay, so let's do an example. In this study, we are trying to assess the effects of teaching methods on reading achievement by comparing the average reading achievement score in different teaching method groups. The data represent reading scores for 12 children being taught under 3 different teaching methods. And remember, the groups being compared are called factors. So our research question is, does teaching method impact reading achievement? So here's our data. This is the score on some achievement test. Method 1, Method 2, and Method 3. So this is one child in this group, Group 1, of 12 kids overall. So you'll see an ANOVA source table, and I just kind of want to tell you what this means. So we have the sum of squares between, and then we have the sum of squares within. We have degrees of freedom k minus 1, where the k is the number of groups. So we have 3 groups, so k is 3, and then n is 12. So k minus 1, so our numerator degrees of freedom would be 2 in this instance, and our denominator for the denominator degrees of freedom would be 12 minus 3, so 9, so 2 over 9. And then we divide the sum of squares between and the sum of squares within, and we get the mean square between and the mean square within, which is the ratio of variance I talked about. And whatever this score is, if the test statistic falls, again, in those tails of the normal distribution, if it's far out enough, then we would say it's significant. So does teaching method impact reading achievement? The null and the alternative hypothesis are like this. The null is mean of 1 is equal to the mean of 2 and the mean of 3, but we're going to just use words. Teaching method does not significantly impact reading achievement. And the alternate is that teaching method does significantly impact reading achievement. You might also see this written at least 1 not equal. So we have the data set up. We have our scores. So we had 0, 4, 0, 4, 3, 7, 6, 4, and that was group 1, so I coded them group 1. There's decimals just because SPSS takes it to do 2 decimal places, but I could have clicked here and told it to just do 1 or none. These are the scores for group 2, and then these are the scores for group 3. I went in here and I value labeled 1 is equal to method 1, 2 is equal to method 2, and 3 is equal to method 3. Then I go to analyze, compare means, and then same place, we've done one sample, we've done independent samples, we've now done paired samples, and now we're doing one-way ANOVA. I click here, and now I've added to the 2 studies we did before, I had score and I have method. So I click on score and I bring it over, and I click on method and I bring it over. Now we have some things we have to choose here. So the first thing we're going to do is to look at post hoc. Okay, so post hoc tests, post hoc is Latin for after the fact. These tell us if we have overall omnibus significance, where the significance is. So when we talk about that at least 1 not equal, that'll tell us that we have an overall significant F statistic, or that our ANOVA is significant. But the next logical question is, well, okay, where's the significance? Is it between method 1 and method 2, or method 1 and method 3, or method 2 and method 3? So what we're going to do is we're going to do a post hoc multiple comparison test. And the easiest one to interpret is this LSD, which is not the drug. It stands for least significant difference. Now we're just going to click that one and we're going to click OK. Okay, so now I've clicked options and this will pop up, and we want descriptive statistics. We want the Levene's test, which is the homogeneity of variance test, and we're going to go ahead and click the means plot. All right, so the first thing we get is we get descriptive statistics, and we can see that we had the mean of 2, a mean of 5, and a mean of 8. Now we want to know, is there a difference among these 3? And then again, if there is a difference, is it between this group and this group, or this group and this group, or this group and this group? Okay, so the test of homogeneity of variance, the Levene statistic, remember, we don't want Levene's to be significant, so we don't want the p to be low. And here it's not, so we can say that before we did anything, these groups were roughly equivalent. All right, then we look to the ANOVA source table. So like I said, between and within, sum of squares between, here are degrees of freedom, here's the mean square. I divide 36 by 4 and I get 9, which is a pretty large F statistic. It's pretty far away from 1. And we see that our p-value is pretty low, so the omnibus, the overall test, is significant. So there is a difference, but now we want to know, where's the difference? Okay, so we look over here and we say method 1 and method 2, and we slide across and we say nope, not significantly different. Method 1 and method 3, we slide across and we say yes, those are significantly different. But we have one more to check. We've checked 1 and 2, we've checked 1 and 3, but now we need to check 2 and 3. And we slide across and we see nope, not significant. So method 1 and 2 are not significantly different, but 1 and 3 are. 2 and 3 are also not significant. And when we look at the means plot, here we are. We've got method 1 and 2, and those are pretty close. And we've got method 2 and 3, and those are almost exactly close. But 1 and 3 are pretty far apart, and that's where we saw the significance. All right, as with everything, we have an effect size, and this is a different effect size. This is a Greek letter eta, so we have eta squared, and it's just the sum of squares between divided by the sum of squares total. So to get the F statistic, we do between and within, but now we want to just to do the effect size, we do between divided by total, which is here, and we see 0.667. And it's interpreted the same way that a coefficient of determination is. So we say teaching method does significantly impact reading achievement. F of numerator comma denominator is equal to 9, p is less than 0.05, eta squared is 0.667, so 66.7% of the variance in reading score is attributed to teaching method. And then we say a least significant post hoc test was conducted, and it was determined that there is a significant difference between teaching method 1 and teaching method 3. And that's it.